Hello and welcome. I am Praveer, and today I'm going to share how to manage the quantum bubble. Note that this is a backup presentation for the Forbes event to take place on January 31st. In this session, I'm going to cover today's quantum computing industry briefly, the basis of the bubble as I see it, some thoughts on redirecting the quantum computing industry and thinking ahead. But I'm going to start with some objectives. So first and foremost is to understand the basis of the quantum computing bubble. But also, in the course of this session, I hope that participants will also see possibilities into some of these important questions. What's the basic idea behind currently conceived quantum computers? Why are superposition and entanglement considered to be so important? On what basis can the quantum computing industry be meaningfully redirected? What is a feasible alternative approach to develop meaningful quantum computers? Why is quantum computing so important? And finally, what are the implications of getting quantum computing wrong or right? So as you go through this session and participate in it, at least with your mind, please think about these questions and how you might answer them, and then we can revisit towards the end. So starting with today's quantum computing foundation, the question, what are some of the ways in which quantum theory has been or is projected to be used? Please think about this for a minute before I proceed. So the promise of quantum theory is substantial, and this is based on the fact that quantum theory has proven to be one of the most fruitful scientific theories in that it has resulted in technology that much of the modern world is indisputably built from. So, as examples, we have concrete devices such as transistors and semiconductors that are at the base of telecommunication and the computing industry. We have applications such as GPS, MRI, and laser, and we have disciplines such as chemistry that have emerged from an understanding of quantum mechanics. So what is it about quantum theory or quantum mechanics that allows such fruitful application? Essentially, quantum mechanics is about the rules governing how atoms behave, interact with each other, and interact with light. And being that atoms are at the base of all matter and even life, a deeper understanding of atoms will inevitably lead to a number of applications. And I will say right now that the number of applications that we have surfaced and that our modern world are built from are just the tip of the iceberg. And there are many, many more applications and possibilities depending on how we really go about practicalizing quantum theory and how we think about quantum theory. Now, a fact is that there continues to be huge investment in the quantum computing industry. And by 2030, this is estimated to be tens of billions of dollars with a compound annual growth rate between 2025 and 2030, pegged at approximately 40%. So based on today's developments in quantum computing, this is what is anticipated to be the growth. And if we are to examine the basis of what's behind quantum computing, and if we can readjust it, as I will suggest in this presentation, perhaps this number grows even higher. So what is the basic idea behind currently conceived quantum computers? I'm going to give you a minute to think about it, and then I'll proceed. So let's look at the basic idea behind currently conceived quantum computers. First and foremost, quantum computers are envisioned to be fundamentally different from digital computers in that they aim to imitate nature. A little bit of background. This was a proposition that was set up by Dr. Richard Feynman, Nobel laureate, and perhaps he can be considered to be the father of the quantum computing industry. But his whole proposition was that we can build computers that, in fact, imitate nature. And this is fundamentally different from regurgitating instruction digitally, as is the case with digital computers. Now, there's also a belief that nature operates randomly. And if that's the case, then that necessitates a probabilistic quantum computer, since probability and statistics are the best way to handle randomness. So that's a key idea behind currently conceived quantum computers. Another key idea is based on the Copenhagen interpretation of quantum mechanics, or close affiliates of that interpretation, in which superposition, a quality which I'm going to speak about in a few minutes, is or can be thought of as unknowable infinite possible states that collapse into one single state when measured. Now, the paradox with this kind of interpretation of quantum mechanics is that while it is thought that any quantum object, that's something that surfaces at the quantum levels, until it is measured, can be an infinite number of possible states, but on measurement, it collapses into a single state that becomes measurable. And by definition, whatever was behind that measurement, or whatever those states were before it was measured, are something that we would never know, because it occurs in a black box. And the only way we will know things is when we measure them. And at that point, they collapse into something that's measurable. And so that's a very fundamental foundation of currently conceived quantum computers, and I'm going to come back to this. Thirdly is the idea of entanglement that has to be created. Again, I'm going to speak about entanglement in just a minute, but briefly, we can think about it as that process by which two quantum objects, when brought into proximity, begin to share properties, become entangled, so as to speak, so that if shifts are made to one of those quantum objects, the second one will automatically, no matter how far away it is, reflect the change that had happened in the first quantum object. The imagined computing power of quantum computers is based on this triple foundation of being able to imitate a probabilistic nature, of the idea of leveraging these properties, these quantum properties of superposition and entanglement, that then give all kinds of computational possibility that is not even conceivable with digital computers. So I had spoken about superposition, but how do you think it might be applied? How can superposition be applied? Well, here's a possible way in which it might be applied. You consider that there are many different skill sets. So you've got a team, or you've got a company that's entering into a new market, or it's facing an unexpected challenge, and there's new knowledge that's required. So the basic idea of superposition is that there are many latent skills that exist in superposed state, and then the act of superposition, due to deliberate computational focus, would allow potentially that state to manifest in the target group, which now has to exercise prowess in that new challenge or new market situation. So if indeed this conception of superposition could be made real, you can see what kind of extraordinary ability it would give in the processing or handling of any kind of situation that we may be faced with. By the way, there is a Forbes article that I had written that goes into this and some other examples in more detail, and you can access that through the link at the bottom. Similarly, entanglement, as I had said, it's when quantum objects come into proximity and somehow now share properties amongst themselves, regardless of how far they are separated, and this sharing happens instantaneously, so even supposedly faster than the speed of light. But one way to think about this practically is that if we have a bottle of water, and whether it's in China or the US, this water would know how to react in similar situations now, no matter how far away it's situated. And again, this suggests a property of entanglement. So the question is practically, how might entanglement be applied? Now, one way practically is consider that there's a controversial or legally volatile situation that the company is faced with. Now, if entanglement between remote teams of employees has taken place, then lessons learned in one place would instantaneously be available in the other place. So that's one kind of practical application of entanglement. That again, if we have theoretically the right kind of device, say that's worn or shared between teams that are remotely located, then somehow lessons learned by one group are instantaneously available to another group. So given these properties of superposition and entanglement, what's a possible computational scenario using quantum computers? Now, one computational scenario is to imagine the future impact an employee may have on a company. So let me break this down. So a company is going to hire a new employee, but the hiring team wants to get a sense of the future impact the employee may have on the company. But there are so many variables in the situation, especially as the employee moves through different stages of the life cycle, right from the hiring to advancing in the organization to perhaps becoming a leader to exiting. There are many, many different variables that would need to be factored in. And the question is, how would the employee, or might the employee get along with others? What kinds of impacts might they have on different situations? How might they influence other potential leaders, and so on? And so it becomes computationally very difficult to establish this upfront. And so this is one example of a computational scenario in which quantum computers could potentially help. So you can see what kind of power it could have as quantum computers are currently conceived. Now, let me just pause here. So what we've done is we've looked at the current quantum computing industry, and we've laid out some of the basics and some of the computational possibilities given these supposed fundamentals of how the quantum level works and how computers that imitate nature or these quantum levels might be able to be applied. But let's think about the basis of the bubble. So here I start with what if. What if superposition and entanglement in fact work differently than imagined? After all, our insight or our perception of superposition and entanglement is based on an interpretation of quantum mechanics, a Copenhagen-like interpretation of quantum mechanics, in which by definition, it's impossible to know what's really happening at the quantum level until you measure something, in which case it collapses into something measurable. And therefore, by definition, these properties that we're saying exist at the quantum level, superposition and entanglement, may work entirely differently than how we think they may work. Further, it may also be the case that entanglement, in fact, never has to be created, because right now our whole assumption with quantum computation is to create this property of entanglement, which then can be translated into computational advantage. But by virtue of all of matter and all of life arising from a single source, that's aka the quantum levels, perhaps everything is already entangled, and there's a different way in which we need to leverage the property of everything already being entangled. And it could be, in this scenario or this perception, that entanglement, in fact, ensures uniqueness. And this we know because no two snowflakes are alike, no two thumbprints are alike. And why would this be the case unless everything was already connected and knew that there was some variation that already existed, and therefore the next thing that had to exist from that subspecies had to be different, and that would only be known if there was some kind of foundational entanglement that was in place. So superposition also might work differently than conceived. And here it could be, because right now, let me just summarize that our current view of superposition is that any quantum object can exist in infinite number of possible states until it's measured, at which point it collapses into some measurable state. But what if superposition is in fact something different, whereby some individual or collective intent that's focused enough acts as a meta function, or in other words, acts as a superposed function for a quantum object that is going to show up. So there's an influence due to the intent that then makes that quantum object show up in a particular way. So this, again, is a different interpretation of superposition. And it could also be that nature is not entirely probabilistic, which is one of the key foundations of today's quantum computation. And I'm going to go into this a little bit more. But if these foundations, that's nature is not indeed entirely probabilistic, superposition and entanglement indeed work differently, then the currently conceived probabilistic quantum computer will simply never deliver. So let's go into this idea of a non-probabilistic nature in a little more detail. The question here is, if nature were probabilistic, why in fact is there abundant order in matter and life? When we probe into layers of matter and life, we see immense order at the levels of quantum particles, at the levels of atoms, at the levels of cells. And in reality, the periodic table in which all atoms are arranged is not so much about a table as about the system behind the table. What it's suggesting is that there is order which in fact dictates how atoms show up. So this thing that's suggested to be entirely random is in fact not random. So as we know, if we look at the quantum particle level, all quantum particles are supposed to exist in one of four categories: quarks, leptons, bosons, and the Higgs boson. If you look at all atoms in the periodic table, there again exist in one of four categories: P shell, S shell, F shell, and D shell atoms. And if you look at all living cells, which have four molecular plans, that is, by definition, any living cell has only four molecular plans, and these are nucleic acids, polysaccharides, lipids, and proteins. But we see that there is this order, and there's also this what appears to be fourfold order, and this certainly requires more investigation to find out if indeed such fourfold order emanates from the quantum levels, which is supposed to be entirely random. So could it be that, in fact, you've got a situation where quarks are related somehow to P shell atoms, which are related somehow to nucleic acids? And these all have a root pattern, which in fact emanates from the quantum levels itself. Now, these are important questions that need to be objectively addressed if we want to, in fact, be true to the aim of quantum computers, which is to imitate nature. So let's think about or look into this reality of nature as a single system. So as we know, all quantum particles are sourced from the quantum level. All atoms are sourced from quantum particles. All molecules are sourced from atoms. All molecular plans are sourced from molecules. So if that's the case, then it's evident that these different layers of matter and life are in fact tightly integrated and should be perceived as one system. So the question is, why don't we study it as a single system, even if we're trying to get insight into the behavior of one layer or the other? So when we're studying quantum level and we want to build a quantum computer that is going to imitate how the quantum level operates, the question is, can we get insight, and can, in fact, the architecture of such a quantum computer be determined by our understanding of how nature, in fact, is a single system, and how there might be insight that's gained about the quantum levels from an understanding of how these fourfold plans show up at the cellular level, which by definition is much more probable and much more experimentable. Now, such an effort was, in fact, executed at a different scale. If any of you are familiar with the book Scale, written by Geoffrey West, in that he's done a remarkable study of looking at similarities between organisms, cities, economies, which in the theory are supposed to operate completely independently, but yet there are laws, there are scaling laws that are true of any of them, which suggest that there might be some root patterns or some ways in which any kind of quantum object or entity created from a quantum object prefers to operate, because that's in fact how it operates as a root process at the quantum level. So this may in fact also propose a different way to build or to understand the architecture of possible quantum computers. And just to summarize, if there's a correlation between living cells and the quantum level, then why wouldn't understanding observations and experimentation at the level of cells provide insight into fundamental dynamics that exist at the quantum level? And again, this would have a huge impact in how we perceive quantum mechanics and how we can build quantum computers. So given that, let me pause here. What could be the basis of the quantum computing bubble? Well, let me summarize the basis based on the discussion that we've had so far, or the session so far. One, the premise on which quantum computation is based is questionable because the problem arises in interpreting or modeling nature. If we assume that nature is probabilistic and that there is a certain way in which superposition and entanglement work, we're going to model a computer that whose aim is to imitate nature in a certain way. But if we interpret nature differently to say that it's not entirely probabilistic, but is to some degree non-probabilistic, and in fact, superposition and entanglement work differently, and there might be other quantum properties that are as important, then quantum computation would, in fact, work differently. So how one sees nature and what active dynamics one attributes to it will likely determine the design and possibilities of any imitating quantum computer, as I just said. And again, just reiterating, if probability, superposition, and entanglement work differently, then the foundation of building a probabilistic quantum computer is called into question. But if all hardware and software efforts, and this is where investment is taking place today, is based on the interpretation of quantum dynamics and an architecture of quantum computers that follows a certain interpretation of nature, then how possibly would it work if that interpretation proves to be different? So it becomes very important to understand the application claims of quantum computers and the rationale of the hardware and software that is going to drive the applications. And this really is the basis of the quantum computing bubble, because in my perception, we have not adequately questioned how nature operates, and we have not adequately questioned the foundation on which quantum computers today are based, that is probabilistic nature, superposition of a certain kind, entanglement of a certain kind. And unless we do so, then investments are in fact going to prove that this perception of quantum computation does not work the way in which it was imagined. So how can we possibly redirect the quantum computing industry? For this, I would turn to the most successful of known quantum computers, the atom. So why is the atom the most successful of quantum computers? Well, first of all, it's comprised entirely of quantum particles. So the nuclei are made from quarks bonded together to the action of bosons, both quarks and bosons being quantum particles. Electrons exist in stable orbits around the nucleus, and electrons are, of course, another kind of quantum particle. We already know that electrons do exist in multiple superposed states, so we already have the reality of superposition happening in an atom. All atoms of the same atomic number exhibit the same properties regardless of where they are. And that means that if you've got an atom of atomic number 47, it's silver, and no matter where silver exists, it's going to act the same way, which means that there's already entanglement that's existing. And further, the lifetime of quantum states, which is such a difficult thing to have endure with our current modeling of quantum computers, in fact, endures, as we see with phenomena of superposition and entanglement as they happen at the level of the atoms. Now, the reason why I would say an atom is a quantum computer is because it's in a continual state of change. So in spite of its stability, it's in a continual state of change due to the interaction it has with photons. And photons, of course, being another word for light. So as any atom is subject to light, it continually changes its state and therefore goes through a process of quantum computation. And therefore, the atom is perhaps the most robust the most stable of quantum computers because we know it operates robustly in a range of environments. We know it's not subject to decoherence, which is a big problem with today's hardware attempts at quantum computing. We know that it's scalable because atoms combine to form complex chains of molecules. And therefore, scalability, in fact, as nature shows us, is the natural law of things. So if nature can build robust, stable, scalable quantum computers, the question is, why can't leading companies? My view on this simply is that we're approaching quantum computation with restrictive biases. And part of this bias comes from the fact that we've had so much success with digital computation, and we continue to witness a plethora of useful applications that we now forget about all the mechanics of what's happening at the quantum level, which already is biased by certain interpretations. But we even think of the possibilities of what can happen with quantum computers in the same way as we think about what we do with digital computers. And so that's part of the problem, is because we're trying to create applications that we already know are possible with digital computers. And so we have a double blindfold on. We have a theory which is restricted by the applications we think should exist, and a theory that's restricted by our biases of how we see nature operating. And if we were to lift these biases, then in fact, we might be able to build a stable, scalable quantum computer. So let's see what we can learn from the atom. Now, first of all, the scalability of atom-based quantum computers combining together to form chains of functional molecules suggests that there's a different mathematics and logic that is happening at the quantum level. And therefore, our approach that's currently founded on this probability qubit-enabled approach would need to be substantially changed. Because the visible does not appear magically out of the invisible. And I'm going to go with this idea of reverse extrapolation. But basically, the idea is that we've got function that we know is embodied by atoms, and certainly there's different function embodied in different molecules. But the idea that you've got, say, silver acting entirely different from gold, acting entirely different from copper, and so on, means that that function must emanate from the quantum level itself. So we have to be able to understand the mathematics of what's happening at the quantum level differently than we now do. That's what this is suggesting. And let me go with this idea of reverse extrapolation. The easiest way to think about this is that when we look at, say, a living cell, let's take a human cell, we know that any living cell comprises of 4 molecular plans. There's nucleic acids, polysaccharides, proteins, and lipids. But for example, if we just focus on proteins, we know there are over 30,000 different proteins in the human cell, and each of these proteins has a precise function. So that means that the form that exists is supporting or is the vehicle for some kind of function that's precipitating in that form. And we see this idea of function, and not just of any function, but of fourfold function, going back to a less complex level of granularity at atoms. And in fact, I've done a lot of writing and research on this idea that there is a tighter relationship than we might imagine between the 4 properties or ways in which molecular plans show up And these are tightly related to the four categories of atoms. So for example, an S shell atom is tightly related to polysaccharides. A D shell atom is tightly related to proteins and so on. And if we go further back, again, we find this fourfold order existing, which is functional. So we find that quarks are, in this point of view, in fact, have a tight correlation with the P shell atoms and with nucleic acids. And the point of this reverse extrapolation is to suggest that these root functions are mathematical and in fact exist at the quantum level. Now, if we were to take this atom-based idea where the atom is the most stable of quantum computers, then we know by definition we're breaking through many existing technological barriers which today's attempt at building quantum computers are facing. So first of all, the size of quantum computers can be radically larger because they're based on photons and atoms that are both known to operate stably at room temperature. As I said before, quantum state lifetimes is enduring because, again, it's based on stable atoms and it will far exceed the qubit lifetime. Gates themselves are not subject to decoherence because they're built using photons and atoms. The functional mathematics, which I actually call F cube mole, and what that stands for is the fourfold functional mathematics of light, is built on the idea of a pre-existing entanglement and superposition as opposed to the idea of having to create these. And if we can leverage these with the right kind of computing device, then we have access to the functional mathematics that also exist at the quantum levels. And so building quantum computers then becomes an entirely different exercise. And as we already know that atoms and molecules already have 100% accuracy in operations, and this is opposed to manufactured qubits, which at the best would have 95% accuracy. And in a computation world, 95% accuracy simply won't fly. So let's think ahead. What could be some of the implications of leveraging atoms, reverse extrapolation, and breaking the technological barriers that I just went through? First of all, there would be an entirely new technology stack, which means that software and hardware, there would be immense potential to build these differently than are currently being built. First of all, at level one, the hardware would be radically more precise based on interpretation of a range of stable atom-based quantum computers, all set in silicon substrate, and leveraging proven approaches such as LED, MRI, laser, GPS. So that's a huge difference from the current basis of how quantum computing hardware is perceived. At level two, control systems would essentially exist to maintain integrity of the F cube mole circuits, so the specific mathematics that is existing at the quantum levels. At level three, you'd have software that's based on F cube mole algorithms, so it's entirely different software. And at level four, importantly, what we would in fact be doing is allowing generation, interpretation, and testing of quantum phenomena through any quantum computer that we're building. And here, as perhaps you can see, and I'm going to go over in a few minutes, but the kinds of applications of quantum computers is entirely different because it's creative as opposed to constructive. So there's a new possible, if we look at, for example, pattern families that currently exist. This is from a study done in 2018, so it's 5 years old, but at that point there were about 14 or 1500 known patents, and which is a very small number, but importantly, on doing a patent research, they were mostly based on the black box approach. And then secondly, based on some research done in 2023, we can see the breakdown of leading companies filing quantum patents, which again, as far as my research has shown, these are again based on the black box or some kind of variation of the Copenhagen interpretation of quantum mechanics. So there's basically a huge opportunity for new quantum patents based on a different technology stack, based on a different perception of what's happening at the quantum level. And there will be many applications in the areas of genetics, medical technologies, material sciences, artificial intelligence, transhumanism. And while we don't have time to go over that right now, this is something that I have written about in some of the books that I've authored on the subject. But I'm going to step back. What really is the importance of quantum computing? So here's my view. Since quantum technology deals with the smallest measurable units, it's flirting with possibilities that escape the eye. So it's on the borderline of what can be considered mysterious. And that's, in fact, where its biggest impacts should come from. It's not about regurgitating what digital computation has already done. We miss the point if we do that. There are, in fact, many processes of nature that challenge our understanding, but clearly exist and have been around for a long time. With superposition and entanglement, we're beginning to make visible what was considered to be invisible. But equally, there are other quantum properties that do exist and which some thought will give insight into. And this really is the importance of quantum computing, is to work with these different properties in the way in which I'm suggesting they should be interpreted here. And this would, in fact, create a whole series of different applications. We need to think about quantum computing, in fact, differently than digital computing. Otherwise, there's no point to really go down a path of quantum computing. So in summary, what's the basis of the quantum computing bubble? We can say that it's due to a triple foundation that might be misplaced. Why are superposition and entanglement currently considered to be so important? Simply because if we look at the schemes of quantum computation, they leverage the interpretation of superposition and entanglement as they exist. What's the basic idea behind currently conceived quantum computers? It's basically the idea of imitating a probabilistic nature and leveraging superposition and creating entanglement. On what basis can the quantum computing industry be meaningfully redirected? By interpreting nature based on the order that we see rather than assuming that it's completely random. Therefore, giving it some basis of non-probability or determinism. And further, in seeing that there are different kinds of applications that need to be built when we're dealing with this veil that separates the visible from the invisible. So what's a feasible alternative approach to developing meaningful quantum computers? It's to use the most successful of quantum computers that nature has already built and shown us, the atom, and to use the atom to perceive what's happening at the quantum level through a different kind of understanding of quantum dynamics. And why is quantum computing so important? Because simply we're dealing with the smallest possible granularity of nature that we can work with. And this means that we have the opportunity to create something that's, in fact, fundamentally creative as opposed to constructive. What are the implications of getting quantum computing wrong or right? Getting it wrong means we're basically creating a bubble and going to waste billions of dollars and just end up doing whatever we've proven and can do with digital computation. Getting it right means that we, in fact, become co-creators with nature to then do something entirely different, potentially. So key takeaways before I wrap up. The quantum computing industry's current trajectory I believe, will lead to an inevitable bubble. There is a lot that can be learned from the most prolific, successful of nature's quantum computers, the atom. And finally, we have not even begun to touch the surface of what is possible with quantum computation, ranging from the technology stack implications to leveraging mysteries hidden by the quantum veil. I conclude with this quote from Dr. Richard Feynman. We are at the very beginning of time for the human race. It is not unreasonable that we grapple with problems, but there are tens of thousands of years in the future. Our responsibility is to do what we can, learn what we can, improve these solutions, and pass them on.